process selection. And from this point on, we will have some chapters in general. We will be discussing some different aspects of additive manufacturing. Since we have done all with the additive manufacturing processes, now you are all aware of different processes we have gone through: film fabrication, stereolithography, digital light processing, selective laser sintering, selective laser melting, and then sheet lamination processes, deposition processes, direct write technologies. So you have, I think, basic knowledge in these additive manufacturing processes. And from now on, we'll be discussing some issues related with all of these processes, not in discussion with specific process, but we'll be discussing the whole additive manufacturing paradigms. And the first one is guidelines for process selection. So we are trying to discuss some guidelines, how we are going to select the best additive manufacturing process for your given task. And as you know, we have additive manufacturing machines, and these machines are used for different purposes. First of all, we use them for visual aids, just to show you the 3D product in physically, and you may have them in your presentations, show that your model is working, your assemblies, your functional assemblies are working, or you may use it for checking whether your part is fitting exactly into your, let's say, other part of the assembly. And you may further use them especially for specific tooling problems in, let's say, manufacturing or in other assembly operations. You may need to have special tools to do your other operations. And additive manufacturing is a fast way, as you know, and especially fused filament fabrication is used for these purposes. And then you may fabricate some patterns to obtain the, let's say, molds for the metal castings. It's another application area. Or lastly, you may use additive manufacturing directly to print, to fabricate your products. And that's why we call it as direct digital manufacturing, or some people call it as direct rapid manufacturing. This time, we're not using the term prototyping, since the resulting product will be the final product, not the prototype. So as you know, we have some constraints in all of these additive manufacturing methods, machines. We should be aware of all these and try to select the best type of approach and best type of machine so that your requirements, your constraints will be satisfied. And these are some constraints on material properties. In some methods, we have less strength, for instance, in specific directions. And additive manufacturing anisotropy is one of the biggest problems. And we, as you know, is quite slower, especially the manufacturing process is slower compared to the conventional manufacturing processes. Its cost might be a bit higher for low amount of production, or it's up to you, up to the number of actually products. And accuracy is not as good as you know, CNC machining, but we have high accuracy, especially in selective laser, stereolithography. For small parts, you can obtain high accuracy and highly detailed geometries. And we can say that right now, additive manufacturing is a bit behind the conventional manufacturing technology. But this gap actually is decreasing every day, and probably in a few years, in maybe 10 years, this gap will be very small. Even maybe they will have the same capabilities in terms of such constraints. And we discussed this issue, but let me remind it once again. We said that speed is low, but once you consider the whole pipeline, whole design and manufacturing pipeline, additive manufacturing is much faster. You can easily go into the market. For instance, if you have an idea and want to produce your product in less than a day, then you can easily do it with additive manufacturing technologies. But if you want to do it with conventional manufacturing, then you need to find a proper company. You need to design some molds, maybe select tools. So it will take at least a week to produce such a new product. And he said that this chapter is about process selection, how we are going to do it. We have some restrictions, we have some rules, we have some knowledge about the process and the machines. So we want to use it in a decision-making software. So we will have a kind of a simple software, and inside this software, behind this software, some algorithms will be running, and they will be checking some types of machines and some processes. And at the end of this, at the output actually of this decision-making software is the cost and the time you need to spend for manufacturing once you use any kind of machine. And they may also assist you in planning the processes, so they are quite useful, especially if you are not aware of all the properties of some specific additive manufacturing technologies. So where you can use the software, you may use it for quotation support. For instance, you may be given a part and then you want to determine which machine is the best choice for this part and which material you should use. So you can, if you're not highly experienced in this field, you can use this decision-making software and try to come up with a solution. Or you may use the software to discuss your capital investments, whether it is feasible or not. And again, the software will give you some options, which machine or which technology is best for your desired, let's say, manufacturing tasks. And lastly, you may use this software to actually do a kind of a process planning. You may decide on how many parts you're going to have in the table, in the bed. This might be actually the outcome of your decision-making software. So in this decision theory, we need to have some options, and from these options, we will come up with some specific solutions. And while we are evaluating them, we need to have some restrictions, some expectations, and lastly, you may have some preferences. Some process or some machine might have other advantages, so you need to consider all these while deciding on a specific machine or let's say a process. So the options are kind of additive manufacturing processes, the machines maybe, the expectations might be different for different obviously technologies, and these are the outcomes of the options. And in the software, in the decision-making software, we need to also have some uncertainties, since you cannot exactly say that one process is 50% much better than the other one. We don't have such exact answers, so that's why you need to always have some uncertainties included in your expectations. And lastly, you have some preferences according to the, let's say, requirements of the decision maker. You can check some answers. For instance, the decision software may give you 3 answers, and then you are the one actually who should decide on the best one. You may check, for instance, the time values, the cost, surface quality of the products, and then decide on the best one. Any questions, guys, up to now about this introduction to process selection? So let's have a look at an example. In this example, we have such a product. This is the solid model of the product, and it is a caster, and it's made of steel. We have a company producing this kind of casters. And customers sometimes say they want to have tens of this product in a different dimensions, or another customer comes and says that they only want to have just a single of this. And again, the dimensions are not the same. Each customer have different dimensions and different numbers of products. So that's why actually they need to have an additive manufacturing machine. Otherwise, it could be quite difficult. It will be quite difficult. They need to do some casting, and for each customer, they need to prepare special molds, special patterns, and that will cost very much to the customers and also to the company. So that's why actually they are planning to switch to additive manufacturing, and with the help of it, they will respond to the needs of customers in a shorter time and in a much efficient way. And they have actually 6 processes under consideration. These are all metal additive manufacturing technologies: direct metal deposition, metal laser sintering, electron beam melting, laser engine net shaping, selective laser sintering, and melting. So these are the 6 processes they can follow if they are going to produce their product. And the material is stainless steel. So we need to also consider the technologies, the machines, in terms of their material capabilities. So what are the dimensions, minimum and maximum dimensions of the given shape? These are some properties of the geometry of the model. We have some minimum and maximum values for these. So customers can select any values in between this minimum and maximum values. And for the internal actually hole, we don't have any flexibility. It's always it has always 12 millimeter diameter, and the length of the balls are 100 millimeters. So you see we have some kind of a table, and in this table they have some properties. For instance, they will consider UTS, the UTS of the resulting part, hardness of it, density of the resulting product, is detailed capability of the process, geometric complexity, build time, and part cost. So we have 2 scenarios. Actually, they will decide on these 2 scenarios, and as we have discussed, we have 6 options, different metal additive manufacturing techniques, and then at the below of this table, we have some extra information regarding these properties. And there's a nice question. I was also planning to ask that. Hussein asked it: can we produce SLS products? So since we said that they have 6 different processes, but you see this one is selective laser sintering. So how can they produce metal parts? They may be using it not direct printing, but they may be using it for obtaining the mold of the casting process. We cannot use selective laser sintering as the main metal additive manufacturing method, since in this one we are simply sintering the powders. But if you sinter the metal powders, then you need to do further operations. So it's not quite possible. We can obtain final products, final polymer products with selective laser sintering. So let's go back to this table. And we said that there are 2 different scenarios. So in the first one, you see we have different importance for different properties. Which one has the highest importance? Yes, geometric complexity has the highest importance. And then we have, I think, yes, cost, build time. And which one is the least important? I think it's the detailed capability of the process. It has the least importance. But if you look at the second scenario, all the properties have equal importance. So that's why there are 2 different scenarios, and we are going to do some multiplication and summation, and then come up with some values for each processes. And then by looking at the scores they got, actually, you can simply decide whether one of them can be used, or maybe we can select 2 of them and then go on with other details. Let's have a look at briefly UTS values, for instance. So we prefer to have obviously high UTS value, and its units is in MPa, and in maximum we can have 2500s, and minimum we can have 500s. So you see the best one is the 4th one. And if you look at hardness, again, we prefer to have high hardness. Again, the best one is 4th. And its density is a bit, actually the 4th one has a bit lower density compared to fifth, sixth, and second and third processes. So these are such details. This part is actually a bit subjective. They have given some scores from 1 to 10, whether this process is capable of printing complicated shapes or not. But this is obviously not an objective evaluation. Then we have another one in terms of build time and part cost. So we have such different properties. Now we are going to do some multiplications with the given importance levels and try to come up with the best solution. So these are the things I mentioned. And you'll see these are the results. So what is the best one? See, the fourth process is the best one. The score is 0753, and then the closest one is the second one. If you take all the actually properties, if all the properties have the equal importance, then again the fourth one will be the best one, best solution, best additive manufacturing process, and the other ones, as you see, have less scores. So what was the fourth one? Let me go through it. I forgot the fourth one. This is laser engineered net shaping process, which was actually a trademark for deposition, metal deposition methods. Any questions, guys, up to now after this scoring?
Hocam weight'ler nasıl belirleniyor kısmını aldık.
According to their scores, these are the scores. How we got them?
Senaryoların weight'leri.
This is, you decide on it actually. Are you asking the values here, the weights of the properties?
Evet.
This is decided by the customer or by the user. It's up to you. It's up to actually your application. For instance, if you are producing a complicated shape, then geometric complexity might be important. But if you want to decrease your manufacturing time, then you may give more importance to build time. Or if the cost is important, you may increase, for instance, this value from 0.19 to 0.25, so that at the end of your evaluation, you will obtain the cheapest process. So it's up to you.
Hocam bir soru da ben sorabilir miyim? Bu puanlamada biz 1 ve 0 gibi mi düşünüyoruz? Yani bu bizim istediğimiz değeri sağlıyorsa o puanı veriyoruz, sağlamıyorsa vermiyoruz şeklinde yapıyorsak. Ama mesela kostu çok yüksek de olabilir.
No, we have probably some, as you see, we have ratio kind of things here. For instance, the lowest UTS value is 500 and the maximum is 2500. So what do? You have a kind of a scale in between. If the UTS value is 500, then you will give 0. But we have 600, so it will be about 0.05. So the score is, this one is going to get, the fifth process will get 0.05, and you will multiply that value with 0.167. But if you consider the fourth process, since it's very close to the maximum value, then its score is around, I think, 0.7, let's say. Then you will multiply 0.7 with this scale. This is how we proceed. Again, in terms of hardness, the fourth one has hardness value of 60, and you see the maximum value is 70, so it's very close to that. You will assign, let's say, 0.85 score for the fourth process, and then multiply it with the scale you have given to this hardness property.
Anladım hocam.
Or let's have a look at the density. The maximum density is 100%, so I will give 1 to 5th and the 6th processes and then multiply with this scales. And lastly, you will sum all these values and obtain such an overall result for each process. Okay, any other questions, guys, and about this evaluation. Okay. So you see, it's not very easy, not straightforward. You need to have some basic information about additive manufacturing processes. You need to define some, let's say, factors, values to different properties. You need to know the relations between several properties. For instance, if you increase, let's say, the material density, then probably your cost will increase. So there are such relations between different properties, and it's quite difficult to decouple them. That's why we try to have kind of an estimate about this selection. Another difficulty in the selection is that sometimes the manufacturers of additive manufacturing machineries may not give you the true results about their machines. And that's why it's better you contact with the existing users and get some information from experienced people. Otherwise, the values in the catalogs may not be correct or not exactly correct, or you may visit such companies in the conventions and the exhibitions and check the results of their products. And another thing, obviously, the selection depends highly on your experience in this field. If you are inexperienced, then probably you will not be able to obtain the best additive manufacturing process for your application. It's better you know the details of all these processes and then later decide on the best process. Now let's have a look at an example software, example system for preliminary selection. They have done it in MATLAB, and they use a graphical user interface of MATLAB. In a moment, I will show you some screenshots. And this software actually computes build times and costs of the machines. And then later, you can decide on the best, let's say, additive manufacturing process. So with the help of this process, with software, we can check which additive manufacturing technology is suitable for our direct digital manufacturing approach. Since if you remember, we said that in direct digital manufacturing, we are not producing prototypes, we are producing the final products. And you may use the same software to determine possible materials for your process, check their building times, build options, and cost of the processes. And furthermore, you can also check life cycle benefits of additive manufacturing, whether you can recycle your parts, products, or any powder you have in the additive manufacturing machinery. They are all possible with the help of this specific software. So you may work on some specific case studies. You may change the size of your design, the number of products to be fabricated. By doing some preliminary, let's say, tests, you can finally decide on which process is best for your application. This is the main flow chart of this software. So at first, we need to define the characteristics of the projects. So what should be the rate of the production, the amount of time you're going to spend for production, what is the part life. For instance, you may need to use the parts for 10 years, for just a year maybe, or for a few months. So they will affect the result of this selection. And also you need to provide some information about the parts, like the size of them, volume, some dimensions, what type of material you are going to use in this part production, the quality, the surface quality you want to have at the end of manufacturing, the tolerances, size of your minimum features. They're all important and they should be given to this software. And then your software will have qualitative assessments about the complexity of your parts, whether you have customization, whether you may have part consolidation. You may decrease the number of parts in your assembly, and it may also give you a kind of a turnaround time, and what is the rate of return of investment. You can determine such kind of things with the help of preliminary assessments. And then once you have these preliminary machines available, you can select some of these and then work on specific machines. Let's say you have selected 3 of these, and then in the next steps, you just focus on 3 machines and try to orient your parts, try to have, let's say, 10 parts, and then you may have another test case where you need to produce hundreds of them. So you may have several cases and try to estimate the build time and the cost of these manufacturing, let's say, steps. And after that, you should have required information and then decide on your own which process and which machine is the best one for your application. Any questions, guys, about this pipeline? This is a summary of the inputs. You need to provide the production rate, how many parts you're going to produce in a week, what is your cost, what's your target cost for the final product, and how long actually you can spend your time in manufacturing. For instance, you may say that I may wait for a day for the production, or you may say that I want to produce this product in just an hour. So this is an important issue since it will highly affect the technology you're going to select and the type of machine you will use in this additive manufacturing application. The other issues we discussed: surface roughness, the volume of the parts, size of them, the tolerances. So they need to be provided into this software. So these are some screenshots of this direct digital manufacturing system. And as you see, at first you need to provide some values for the part, the size of it, actual volume, the type of material you are going to use, surface finish you want to have, feature sizes, tolerances. So they're all given at this initial step of the software. And then you have some kind of qualitative assessments. There are some questions and you need to answer them according to your application. For instance, what is your first fast turnaround? How quickly do you have to respond to design changes and customer orders? It says that 2 to 4 days is quite acceptable. For instance, what is the geometry complexity? Part shape could be fabricated using 5-axis mill if you follow in conventional machining. So depending on these selections, the software assigns some values, some scores to the machines, and later it will give you some possible machines which can be used in your application, and then you will decide on them. So these are the result of your qualitative assessments. And then what you do, it's actually this software requires you to select some types of machines. So according to your qualitative assessments, these are the feasible machines. So first, in the next step, we will have further assessment, and for that further assessment, it wants you actually select some specific type of machines from this, let's say, set of machines. Here you see we have feasible ones and infeasible ones. Obviously, it's better you not select, but to make a fair comparison, you may select an infeasible one from also this group. And then later, what this software does actually is that since you have provided the information regarding your parts, it checks how many parts can be produced on this machine, what is the surface quality. So it performs such further calculations, further assessment, and give you some results. So what are the results? The results are the build time and the cost. If you look at the first one here, first plot, let's say kind of bar graph, we have 4 machines selected, and this is the time spent. You need the time you need to manufacture for the same number of parts. This is the blue ones are the minimum times estimated, and the red ones are the maximum. And obviously, you can see that this second machine, center station, HIQHS, is the best one. And this one is also quite okay, but the other two are not good for your application. And regarding the cost, this is the cost per part actually, and it's in terms of dollars. We have operation costs, purchase costs, maintaining costs, and material costs. And obviously, if you look at it, the second one is again the best choice. It even doesn't have any maintenance costs. Probably it's a very simple machine. And if you look at, for instance, the first one, SLA Viper, it is a high cost for the operation. But as we said, the second one is best in terms of any cost, let's say, category. But we also have a bit better one. The fourth one is almost equal to the second one. But if you look at the time, this one, the fourth one has disadvantages compared to the second one. So that's why we can simply say that the second type of additive manufacturing machine is much useful for our application.